podcast was created as a supplemental learning resource for our cognitive psychology course. The content is based on course topics and readings from Essentials of Cognitive Psychology by Christopher Klein, along with instructor-developed explanations, examples, and pedagogical framing. AI tools were used to help transform course material into a conversational podcast format, including the use of AI-generated voices. The use of AI voice technology is intended to make the material more engaging, accessible, and flexible for students. However, the podcast should not replace careful reading of the textbook, reviewing course materials, or completing assigned activities. Any interpretations, examples, or explanations included in the podcast are provided for educational purposes and are the responsibility of the instructor. Students should rely on the assigned textbook, course lectures, and official course materials as the primary sources for exams, assignments, and class discussions.
We have all been there. You're trying to log into like a student portal or a bank account, and the screen asks you for that two-factor authentication code.
Oh, yeah, every single day.
Right. So you grab your phone, the text message pops up, and you see the 6 digits. Let's say it's 48271. 9.
Okay, I've got it.
So you put your phone down, you turn back to your laptop keyboard, and you are frantically repeating it in your head. 48271 48.
And right at that exact fraction of a second, your roommate walks in.
Exactly. They walk in and ask, like, hey, did you leave the stove on? And poof, it is gone.
Completely gone.
The code is just completely evaporated from your mind. It's not, hiding somewhere in the back of your brain. It is fundamentally wiped, as if it never existed at all. And you have to pick up the phone and look all over again.
It's a remarkably universal experience, honestly. And it illustrates this really fascinating structural limitation of human cognition.
Which is what we are getting into today.
Right. Because that feeling of a thought just, vanishing into thin air, it isn't a glitch in your brain. It's actually the system working exactly as it evolved to work.
The numbers from that text message basically didn't make it past a very specific, highly restricted checkpoint in your mind.
Yes. And today, we're unpacking the architecture of that exact checkpoint. We're doing a deep dive into the core concepts of Chapter 4, which is short-term and working memory.
Which is huge, because this is the space where your conscious thought actually happens.
It really is. It's the workspace of the mind.
And if we think about the journey of information through the mind, right, which is the broader narrative of this whole cognitive psychology course you're taking, we've already explored perception.
Right, how our senses take in that raw data from the world around us.
Exactly.
Yeah.
And we've explored attention, how we filter that data and focus on what actually matters. So now we are at the next critical juncture.
Yeah, once you perceive something and you actually pay attention to it, where does it go? What is the actual machinery of the conscious present?
That's the perfect way to phrase it. And we really want to stress to you, the listener, that this deep dive is an audio companion. We're here to help these concepts click for you, but it's not a replacement for actually reading Chapter 4.
Oh, absolutely not. You still have to do the reading and the practice activities, but this will definitely help synthesize it.
So to understand how psychologists map this territory, we kind of have to look at the historical shift in how the field even conceptualized memory in the first place, right?
We do. For a long time, the dominant metaphor in psychology was this passive storage box.
Like a literal filing cabinet.
Yeah, exactly like that. The assumption was that information comes in, you stick it in a short-term holding cell, and eventually maybe it gets filed away into a long-term archive.
It was viewed as a relatively static, almost boring process.
Right. Which brings us to the foundational blueprint of that era, the 1968 Atkinson and Shiffrin modal model of memory.
The modal model. This is usually the first major framework anyone encounters when studying cognition.
It really is the classic starting point. They mapped memory as a strict linear sequence of 3 distinct stages, almost like a factory assembly line.
Okay, so what are those 3 stages?
Information enters sensory memory first, then it moves to short-term memory, and finally, if it survives that far, it reaches long-term memory.
Let's break those down. That first stage, sensory memory, I feel like that one is often misunderstood by students.
It definitely is, because when we use the word memory in everyday life, we're usually talking about like recalling a childhood vacation or remembering the capital of France.
Right, we don't think of the lingering echo of a sound or the afterimage of a bright light as a memory.
But biologically and cognitively, it is a memory. The moment information hits your visual or auditory receptors, it lands in this highly transient sensory storage.
And it's incredibly high quality, right?
Yes, the defining characteristic of sensory memory is its unedited, perfect fidelity, coupled with this extraordinarily rapid decay rate.
It holds a perfect snapshot of reality, but it fades in a matter of seconds, or even like fractions of a second.
Exactly. And the auditory version of this is something everyone has experienced. It's called the auditory double take.
Oh, I love this example.
Right. Imagine sitting on the couch, completely zoned out, maybe scrolling through your feed on your phone, and someone in the room says something to you.
And because your attention was elsewhere, you look up and say, what?
But then, and this is the crazy part, before they can even draw a breath to repeat themselves, you suddenly know exactly what they said.
Yes. You actually answered their question before they can say it again. It makes you feel a little ridiculous.
It does. But that is your echoic memory, which is the auditory component of sensory memory in action.
So what's actually happening in the brain there?
Your brain essentially maintained a 2 to 3 second high-resolution audio recording of their voice.
Even though I wasn't paying attention.
Even though you weren't paying attention. When you suddenly shifted your attention to the fact that someone was speaking, you essentially hit playback on that decaying echo.
That is so cool.
You listen to the recording in your mind, and you process the meaning just before the trace disappeared entirely.
I always think of the visual equivalent, which is iconic memory, like writing your name in the air with a sparkler on the 4th of July.
Oh, that's a perfect analogy.
You see a continuous trail of light hanging in the darkness, even though the sparkler itself is only in one specific physical location at any given millisecond.
Right, your sensory memory is holding on to the light's previous positions just long enough for your brain to perceive a continuous shape.
But obviously, that light trail vanishes instantly.
Instantly.
So if sensory memory is this incredibly brief, and short-term memory is the next step on the assembly line, how long does information survive once it crosses the threshold into short-term memory?
Well, once information passes through the gate of attention and enters short-term memory, its lifespan does increase, but really only slightly.
Wait, really? How slightly?
Without any active effort to maintain it, information in short-term memory typically degrades and disappears within about 15 to 30 seconds.
15 to 30 seconds. That is the baseline biological duration.
That's it. That is the limit of this specific neural workspace.
See, a 30-second absolute limit seems completely counterintuitive when you consider everything we manage to learn and retain as humans.
It does sound impossibly short.
If the system naturally flushes everything out in a half a minute, how does any piece of information, like a historical date, or a math formula, or a new friend's name, how does it survive long enough to become a permanent, lifelong memory?
So the mechanism that bridges that 30-second gap is rehearsal.
Rehearsal, like repeating the authentication code.
Exactly. When you were frantically repeating that two-factor code 482719, you were actively refreshing the decaying neural trace.
So I was essentially resetting the 30-second timer over and over.
Precisely. Rehearsal isn't just about keeping the information alive in the present moment. It actually serves as the transfer mechanism in the Atkinson-Shiffrin model.
Oh, I see.
By continuously looping the information in short-term memory, you are gradually encoding it into the third and final stage, which is long-term memory.
And long-term memory is where capacity and duration are practically infinite, right?
Right. But getting it there is the hard part, because the bottleneck isn't just time.
It's not just that it fades quickly.
No, it's also physically constrained by how much data it can hold simultaneously. And you really can't discuss cognitive capacity without running into George Miller.
Oh, yes. George Miller's famous 1956 paper. This is a huge concept for undergrads to grasp. He introduced one of the most famous phrases in all of psychology.
The magic number 7, plus or minus 2.
Plus or minus 2. So basically 5 to 9.
Exactly. Miller's research aggregated data from numerous experiments on human information processing, and he consistently found this severe bottleneck.
Regardless of what they were trying to remember.
Regardless, whether people were asked to remember sequences of tones or lists of numbers or strings of random letters, their performance would reliably plummet once the list exceeded about 7 items.
It's like the human short-term memory system is just biologically capped at holding between 5 and 9 isolated pieces of information.
It is. But this is where things get a little tricky for students because the definition of an item isn't like an objective physical law.
Right. What counts as an item?
It's entirely dependent on the person perceiving it.
So if I tell someone the limit is 7 items, they might assume they can only hold 7 random individual letters.
But if an item is just a unit of meaning, the brain has this incredible built-in workaround.
And that workaround is a cognitive process called chunking.
Chunking, yes. We expand the functional capacity of our short-term memory by taking small, disparate pieces of information and binding them together into larger, meaningful wholes.
You essentially compress the data.
Exactly.
A classic textbook example really clarifies the mechanics of this.
Hmm.
Imagine staring at a sequence of digits. Ready? 1, 2, 2, 5, 1, 9, 8, 5.
Okay. Treat it as isolated numbers, that is 8 separate items.
Which is pushing right up against the upper limit of Miller's magic number.
Yeah, if you try to hold those 8 random digits, your mental workspace is almost entirely full.
But look at those exact same digits with a different organizational lens. 12-25-1985.
Right. By recognizing that sequence as December 25th, 1985, you haven't changed the raw sensory input at all. It's the same numbers.
But what you have done is accessed your long-term memory, retrieved the structural template for a calendar date, and applied it to the incoming data.
You've compressed 8 distinct items into just 3 chunks: a month, a day, and a year.
And suddenly, instead of taking up 8 slots in your short-term memory, the information only takes up 3 slots.
Leaving you plenty of cognitive bandwidth to process other things. It's brilliant.
It's the neurological equivalent of, like, zipping a computer file before emailing it. You reduce the file size by finding patterns.
And this brings up a really fascinating dynamic. To successfully navigate the limitations of short-term memory, you are entirely dependent on the vast archives of your long-term memory.
Oh, wait, say more about that.
Well, you can't chunk those numbers into a date unless you already know what a calendar date looks like, right?
Well, of course. If I
Right.
didn't know the Gregorian calendar, those are just random numbers to me.
Exactly. This reliance on prior knowledge was beautifully demonstrated in Chase and Simon's 1973 chess experiment.
This is a cornerstone study in understanding expertise. I love this one.
It's so elegant. They wanted to investigate how short-term memory functions differently in novices compared to grandmasters.
So what was the setup?
The methodology was straightforward. They would show both groups a chessboard arranged with pieces for a very brief period, cover it up, and ask them to reconstruct the board from memory.
Okay, pause for a second if you're listening and think about this. If short-term memory is just a biological box limited to 7 items, the grandmaster and the novice should have the exact same performance, right?
Right, the novice remembers 7 pieces. The grandmaster remembers 7 pieces.
But that isn't what happens, assuming the pieces are arranged in a specific way.
Precisely. When Chase and Simon arranged the pieces in configurations that would naturally occur during a real competitive chess game, the grandmasters possessed near-perfect recall.
They could just rebuild the whole board.
Flawlessly, far outperforming the novices.
But the genius of the study was the twist, the control condition.
Yes, they took those exact same chess pieces and scattered them completely randomly across the board in ways that violated the rules and strategies of the game.
And in that random condition, the grandmaster's superior memory completely evaporated.
They performed just as poorly as the beginners. They couldn't remember more than a handful of piece locations.
So what is the underlying mechanism there? Why does their expertise just disappear when the board is randomized?
It reveals that the grandmasters didn't have biologically larger short-term memories. They simply had better compression algorithms.
Better chunking.
Yes. When a master looks at a real game board, they aren't memorizing the coordinates of an isolated pawn or a single knight.
They're seeing the whole battlefield.
Right. Their long-term memory immediately recognizes complex offensive and defensive patterns they've studied for thousands of hours. They see a Sicilian defense or a specific pawn structure.
So they chunk dozens of individual pieces into a single massive strategic concept.
Exactly. But when the pieces are randomized, those long-term memory templates are completely useless. There are no patterns to recognize.
The master is forced to process every single piece as a separate, meaningless item.
And they immediately crash into the exact same cognitive ceiling as the novice, the magic number 7.
We do this constantly in our daily lives without noticing. Think about how you memorize a new license plate. You might spot your initials in the letters or recognize the numbers as, like, your childhood zip code.
You are actively scanning incoming data for patterns you already know so you can chunk it down.
And while chunking solves the capacity problem, the Atkinson-Shiffrin modal model still possessed a fatal theoretical flaw.
It did, framing short-term memory as merely a sequence of storage boxes where information just sits passively until it is either rehearsed or forgotten. It failed to account for the actual mental labor we perform every day.
Right, think about doing a mental math problem. If I ask you right now to multiply 43 by 6 in your head,
Okay, I'm doing it.
you aren't just holding the numbers 43 and 6 in a storage locker. You have to actively break them apart.
Right, I multiply 40 by 6 to get 240, and I have to hold that new number in a temporary mental slot.
Then you multiply 3 by 6 to get 18, hold that in a different slot, and then retrieve the 240 and add them together.
You are manipulating, transforming, and updating information in real time. A passive storage box cannot do that.
That friction. The inability of the modal model to explain complex cognitive tasks like reasoning, language comprehension, and mental arithmetic that led Alan Baddeley and Graham Hitch in 1974 to propose a radical paradigm shift.
They argued that short-term memory isn't just a waiting room, it's an active processing system. And to reflect this dynamic nature, they rebranded it working memory.
The shift from short-term memory to working memory is like the difference between a tiny storage closet and a busy kitchen counter.
I love that analogy.
The storage closet just holds boxes, but the kitchen counter is a workspace. You bring raw ingredients, the sensory information, out onto the counter. You fetch older ingredients from the pantry, your long-term memory, and place them on the counter too.
And then you actively chop, mix, and combine them.
Exactly. Baddeley and Hitch didn't just rename the system. They proposed that this kitchen counter isn't one flat surface, but rather a multi-component system with highly specialized zones.
Yes. Their original 1974 model divided working memory into 3 distinct subsystems: 2 specialized storage buffers, and 1 central control mechanism.
Let's name them.
The storage buffers are the phonological loop, which handles verbal and auditory information, and the visuospatial sketchpad, which manages visual and spatial data.
And governing both of these is the central executive.
Correct.
Let's isolate that first buffer, the phonological loop. This is the part of your mental workspace dedicated exclusively to sound.
So if you are repeating a phone number or trying to remember a person's name you literally just met, you are relying heavily on this loop.
The phonological loop consists of 2 interacting parts, right?
Yes. There is a phonological store, which acts almost like a literal loop of audio tape that can hold about 2 seconds of sound before it fades.
Okay, a 2-second tape loop.
And there is an articulatory control process, which is essentially your inner voice. When you repeat a word in your head, that inner voice is re-recording the audio onto the fading tape loop to keep it active.
What's deeply counterintuitive about this system is how it processes written text. You would assume that reading a book is a purely visual task.
Because you were looking at visual symbols printed on a page.
Right, but research demonstrates that the phonological loop aggressively intercepts that visual data.
The foundational evidence for this is R. Conrad's 1964 experiments on what is known as acoustic confusion.
Acoustic confusion.
Conrad wanted to see what happens when the working memory system is forced to process items that sound very similar.
Let's recreate the logic of that experiment for the listener. If you are listening to this, I'm going to read you a short list of simple one-syllable words. Try to hold them in your mind and repeat them back to yourself. Ready?
Go for it.
Car, rig, scene, bar, rose, pop.
Generally, people find that fairly easy to hold on their mental kitchen counter.
Okay, now let's clear the counter and try a second list. Hold these in your mind. Leak, feed, beak, deep, heat, peak, beat.
In Conrad's research, participants performed significantly worse when trying to recall that second list in order.
Significantly worse.
Oh, yeah. They would frequently stumble, substitute words, or just lose the sequence entirely.
But both lists are just simple English words. They are roughly the exact same length. So why does the brain struggle so severely with the second list?
The second list, leak, feed, beak, deep, heat, peak, beat, shares a repeating phonological characteristic, the long E vowel sound.
They all sound alike.
They sound alike, and here's the kicker. Even when participants in these types of studies are silently reading the words off a visual screen, they still experience this acoustic confusion.
Wait, so the visual shape of the word doesn't matter?
Not to working memory. Your brain automatically translates the visual text into an auditory format via subvocalization. You generate an inner reading voice.
And because those words share the same acoustic properties, their sound traces bleed into each other on that 2-second mental tape loop.
They jam the system. The first list, car, rig, seam, bar, has distinct contrasting vowel sounds, so the audio traces remain separate and clear.
This means that even if I am sitting in a dead silent library reading a textbook without moving my lips at all, my working memory is treating those printed paragraphs as a symphony of sound.
It absolutely is.
Try to read a sentence right now without hearing the words spoken in your own mind. Try to just absorb the meaning of the visual shapes without the inner narrator. For most people, it's virtually impossible.
We are entirely bound to this acoustic translation process.
Why is that?
Well, from an evolutionary psychology perspective, this makes perfect sense. Homo sapiens have possessed spoken language for tens of thousands of years. The neurological hardware for processing speech is deeply ingrained in our biology.
But written language is new.
Written language is a relatively recent human invention, only a few thousand years old. We don't have a dedicated reading center in the brain that evolved independently.
So we basically hack our own brains.
Exactly. We piggyback reading onto our ancient auditory architecture. We force visual symbols through the phonological loop.
Okay, so the phonological loop handles the inner voice and the tape loop of sound. But what happens when we actually do need to process pure visual imagery? Like remembering the layout of an apartment or giving someone directions using a mental map.
Because that data definitely doesn't fit on an audio tape.
Right.
That information is routed to the second storage system in Baddeley's model, the visuospatial sketchpad.
It's Sketchpad.
This component allows you to hold and manipulate visual images and spatial relationships. And just as Conrad proved the existence of the phonological loop by overloading it with similar sounds, other researchers proved the existence of the sketchpad by overloading it with simultaneous spatial tasks.
The classic demonstration of this is Lee Brooks's 1968 experiment involving a block letter F. This is a vital piece of research for undergrads to understand cognitive bottlenecks.
It's such a clever design.
Brooks asked participants to visualize a giant uppercase block letter F in their mind's eye. Imagine it drawn with thick, solid lines.
Okay, I'm picturing it.
Then, starting at the bottom left corner of the letter, participants had to mentally trace their way around the perimeter.
And at every single corner they encountered, they had to make a judgment. Is this an outside corner pointing away from the center of the letter or an inside corner pointing inward?
The act of holding the image of the F and mentally navigating its borders is a heavily spatial and visual task. It demands substantial resources from the visuospatial sketchpad.
The brilliance of Brooks's methodology was how he manipulated the way participants reported their answers.
What were the conditions?
In one condition, participants had to physically point to their answers. They were given a piece of paper with the words outside and inside scattered randomly across it.
Okay.
As they mentally traced the corners of the F, they had to locate the correct word on the paper and point to it with their finger.
But pointing is also a spatial task. You have to coordinate your hand in physical space to target a visual location on a page.
Exactly.
So you have the mental tracing task happening in the sketchpad and the physical pointing task also requiring the sketchpad. What was the alternative condition?
In the second condition, instead of pointing, participants simply spoke their answers out loud. As they mentally traced the corners, they just said the word outside or inside.
Okay, let me guess the outcome here based on the architecture we just established. The participants who had to point probably struggled immensely because they were forcing the brain to do two spatial tasks simultaneously, which crashes the sketchpad.
That is exactly what the data showed. The pointing task resulted in dramatically slower response times and far more errors.
Wow.
The visuospatial sketchpad has a strict capacity limit. When you try to force it to maintain a complex mental image while simultaneously guiding a finger through physical space, the system becomes dangerously overloaded.
The two tasks literally interfere with each other because they're fighting for the exact same cognitive resources.
But the participants who spoke their answers out loud performed much better, because speaking routes the reporting task through an entirely different bucket.
The mental tracing stays in the visuospatial sketchpad, but the speech production is handled by the phonological loop.
Right, because they are separate, independent buffers on the mental kitchen counter. They don't interfere. You can chop vegetables on the cutting board while something else boils on the stove.
This architecture, the existence of separate domain-specific capacity limits, explains a tremendous amount of human behavior, particularly when it comes to multitasking. It is the precise cognitive reason why texting while driving is so inherently dangerous.
It really is. Driving a vehicle is a massively demanding visuospatial task.
You are monitoring lane position, vehicle speed, the distance of the car ahead of you, scanning for pedestrians.
It consumes nearly the entirety of your sketchpad's bandwidth. So if you attempt to read or type a text message, which requires shifting visual focus and spatial coordination to hit the keys, you are trying to draw from a bucket that is already completely empty.
So the system just, inevitably drops information. You will literally fail to perceive the brake lights of the car in front of you because the visual spatial workspace cannot render both realities simultaneously.
But you can usually drive a car and listen to an audiobook at the same time, because the audiobook draws from the phonological loop, leaving the sketchpad free to manage the road.
So we have these two separate workers in the kitchen. The phonological loop handling the audio, and the sketchpad handling the visual geometry. But who is managing the kitchen?
Ah, the boss.
Right. Who decides when to chop, when to stir, and when to completely abandon the meal because the oven is on fire? That brings us to the third component of Baddeley's model.
The central executive.
The central executive.
The central executive is the most complex and arguably the most important component of working memory. It is the cognitive management system. And the most critical thing to understand about the central executive is what it does not do.
Which is?
The central executive does not store any information. It has zero storage capacity of its own.
So it's pure control. It's like a traffic cop at a busy intersection.
That's perfect.
The traffic cop doesn't drive the cars, and the cop doesn't hold the cars in their pockets. The cop simply directs the flow, deciding who gets to move into the intersection, who has to wait, and which lanes need to be shut down.
A very precise analogy. To break down exactly how this traffic cop operates, cognitive psychologists, notably Miyake and his colleagues, in a highly influential year 2000, paper identified 3 specific, distinct executive functions:
Or are they?
shifting, updating, and inhibition.
Let's explore the first one, shifting. This is the ability to disengage your attention from one set of rules or one task and smoothly transition to another.
Right. So if you are sitting at your desk writing an essay and your phone buzzes with a text from a friend,
Your central executive has to disengage from the linguistic commands of the essay, shift the workspace to process the social context of the text message, and then shift back to the academic tone of the essay.
and that shifting carries a metabolic and temporal cost. It is not instantaneous.
There's a lag.
Every time the central executive is forced to switch contexts, there is a micro delay as the new rules are loaded into working memory.
This is why constant task switching destroys productivity. The central executive is spending all its energy reconfiguring the workspace rather than actually processing the information.
Exactly. Now, the second function is updating. This isn't just about switching tasks. It's about constantly revising the contents of the workspace while staying within a single task.
Like we talked earlier about doing mental math, adding up prices in a grocery store aisle.
Right. If you add a $4 coffee to a $3 muffin, you get 7. The central executive has to actively instruct the system to drop the 4 and the 3, hold the 7, and prepare for the next number.
It is constantly monitoring the incoming flow of data, determining what is currently relevant, and relentlessly purging old information to free up capacity.
Because if the central executive fails to update, you get stuck holding on to outdated numbers, and the calculation completely fails.
Which leads us to the third function, inhibition. This is perhaps the most socially and behaviorally critical role of the central executive.
It really is. Inhibition is the deliberate, conscious suppression of a dominant, automatic, or habitual response. It is the braking system of the mind.
Our brains love autopilot, don't they?
Oh, they prefer it. As we navigate the world, we build up massive repositories of habitual routines in our long-term memory. Because relying on habits saves an enormous amount of mental energy. It's highly efficient.
When someone says, "How are you?" Yeah, you don't actually evaluate your physical and emotional state. Your autopilot instantly retrieves the script, "Good, how are you?" and fires it off.
But there are constantly situations where the environmental context demands that we override those automatic scripts. That intervention requires the central executive to exert top-down control, to actively suppress the habit.
This perfectly explains one of the most universally embarrassing social interactions.
Oh, I know where you're going with this.
You walk into a movie theater, hand your ticket to the usher, and they tear it and say, "Enjoy your movie." And before you can stop yourself, your mouth confidently replies, "You too."
It is a textbook failure of executive inhibition.
It haunts me.
Your entire life, the phrase, enjoy your meal or have a good trip, has been met with the polite social script, you too. The brain has heavily reinforced that neural pathway. So when the movie Usher says enjoy, your autopilot cues up the standard response. To prevent you from saying it, your central executive has to actively intervene.
It has to rapidly assess the context, realize the usher is working and not watching a movie, and hit the brakes on the phonological loop before it executes the speech command.
Yeah.
When you accidentally say you too, it means the traffic cop fell asleep at the wheel and let the wrong car speed through the intersection.
Exactly. And what's vital to recognize is that executive control is incredibly fragile because it is so energy dependent.
Explain that. Why is it so fragile?
Well, the central executive relies heavily on the prefrontal cortex, which is a highly metabolically demanding region of the brain. When you are sleep deprived, or when you are experiencing high levels of stress or emotional turmoil, the available resources for executive control plummet.
Which means your ability to inhibit automatic responses drops dramatically.
Dramatic.
This is why, when you are exhausted after a terrible day, you are much more likely to snap at someone in anger, or impulsively eat an entire sleeve of cookies, or doom scroll on your phone instead of doing the reading you plan to do.
Your working memory isn't just a cold calculator for math problems. It is the system that governs self-control. When the central executive is drained, the autopilot takes over, for better or worse.
Wow, that is such a crucial takeaway. This architecture of working memory, the limited storage buffers managed by a vulnerable executive controller, is the fundamental bottleneck of human thought.
It dictates how much we can learn, how effectively we can solve problems, and how well we navigate our environment.
So, to synthesize this overview of Chapter 4, let's trace the arc of what we've covered today.
Good idea. Let's recap.
We began with the realization that memory isn't just an archive, it's a dynamic workspace. We looked at the Atkinson-Shiffrin modal model, understanding how high-resolution sensory memory feeds into a highly constrained short-term memory bottleneck.
And we explored how George Miller quantified that bottleneck with the magic number 7, and how chunking allows us to hack the system by using long-term knowledge to compress incoming data.
Like the chess masters.
Right, like the chess masters. From there, we examine the necessary paradigm shift to Baddeley and Hitch's multi-component working memory model.
We explored the domain-specific nature of the workspace, the phonological loop with its susceptibility to acoustic confusion,
And the visuospatial sketchpad with its vulnerability to spatial interference, like the pointing experiment.
Exactly. Finally, we detailed the central executive, the non-storage control unit that shifts attention, updates the workspace, and inhibits our deeply ingrained automatic behaviors.
It's an incredibly elegant, if fragile, system.
Now, a crucial reminder. While this conversation is designed to help you conceptualize the architecture of your mind, this audio overview is a learning companion.
Yes, please remember that.
It is not a replacement for actually reading Chapter 4 in your textbook, reviewing your lecture notes, and completing the course activities. Engaging directly with the primary material is how you build the long-term memory structures needed to chunk this information on an exam.
And as you move forward, I really encourage you to consider how this biological architecture interacts with the modern environment. We discussed how working memory has strict capacity limits for both visual and auditory information.
Right.
Today, we are surrounded by devices designed to outsource those exact functions. We no longer need to hold phone numbers in our phonological loop or spatial maps in our visuospatial sketchpad. Our smartphones hold them for us.
It raises a profound question about the future of human cognition. Are we freeing up our central executive to focus entirely on higher-order problem-solving and creative shifting? Or, by refusing to exercise our cognitive kitchen counter, are we letting the fundamental workspace of the human mind slowly gather dust?
It's definitely something to think about.
The next time a two-factor authentication code vanishes from your mind because of a slight distraction, take a moment to appreciate the fragile, beautiful machinery working furiously inside your head. Keep questioning the invisible processes that define your reality, and we'll see you next time on The Deep Dive.